Okay, so today we're going to talk about approximating definite integrals. So far we've learned many techniques for handling different types of integrals, but the fact of the matter is that we still can't integrate most functions, right? The functions that I give you that you can use U substitution or integration by parts or partial fractions or a trig substitution are very special functions that have been put together just so that you can use one of those techniques. Okay. So our techniques for approximating areas under a curve by using rectangles, right rectangles, left rectangles, and midpoint rectangles are pretty important. But there are other shapes that we can use that can get us even better approximations than rectangles. We will study them in this section. So my notation I'm going to use is left n and right n, and that stands for Riemann sums using left and right rectangles, n of them, n left and right rectangles. So if I want to approximate the integral from 1 to 3 of 3x squared dx, that is, approximate the area under 3x squared from 1 to 3, I want to use left 2 and right 2. So two rectangles using left endpoints, two rectangles using right endpoints. And I'm going to shade my rectangles in the diagram. So from 1 to 3, if I'm going to do left 2, so here's 1, 1, 2, 3. I'm going to break it into two intervals because they told me to use two rectangles. So here's my first interval, and then I'll use another color for my second interval. All right, so I have to build a rectangle on top of each of those intervals. If I use a left endpoint, that means that determines the height of the rectangle. So you go to the left endpoint of your interval, go up to the function, and that's the height of your rectangle. And then for the other one, up to the function, height of your rectangle. So this pink rectangle here, it's got base of 1. What's its height? 3, because you plug 1 into the function to get the height of this thing. So that would be 3. So 3 times 1 is 3. And then for my green rectangle, its base is 1. What's its height? 12, yeah, because we take the 2, plug it into my function. That tells me the height of the rectangle. 2 squared is 4, times 3 is 12. So my approximation under this curve using left 2 is 15. 3 plus 12. All right, so then I'm going to do it also using right endpoints. Same thing, I'm going to mark my intervals, two intervals, from 1 to 3. But this time I create the height of the rectangle using the right endpoint. Okay, so this pink rectangle, now it's going to have an area of 12. And then my green rectangle, it has a height of, I got to plug a 3 in. 3 squared is 9, times 3 is 27. So right 2 is going to be 12 plus 27, which is 39. Okay, so now those are things we already knew how to do, right? We've done that before. So now we're going to approximate that same area, again using two intervals, but I'm going to use trapezoids. Instead of a rectangle, I'm going to use a trapezoid over each interval. So this diagram on the left here, I'm going to mark my two intervals, 1 to 2, 2 to 3. And then instead of using a rectangle that has a constant height, I'm going to create a trapezoid so that I'm approximating this curve with a straight line. Trapezoid, it's not too hard to find the area of a trapezoid. It's a little harder than a rectangle, but not too bad. And then same thing over here, go up to my curve on the left and the right, and connect them with a line. Okay, do you guys remember the area formula for a trapezoid? Close. Colder. So it's that you have to do the area of the triangle part, which is 1/2 base times height, plus the area of the rectangle part. So, and I won't derive the whole thing. Its area is 1/2 the sum of the bases, right? So not multiplied, but added, times the height. So my pink trapezoid here, my bases are these two different heights there. So one is going to be f of 1 and the other is going to be f of 2. Okay, so this height is 3 and this height we know is 12. And then this is we normally think of this as the base, but it's the height of the trapezoid, which is a 1. So that ends up being 7.5. Is that right? I could always check. I'm not sure if that's, I'm just going to double check by doing this. So this is a height of 3, so that's 3. And then this triangle, that whole thing's 12 minus 3, so this is 9. So this is 4.5. Yeah, 7.5. All right, and then the area of this blue one, 1/2. Some of these bases, which is 12 plus 27, times the height, 1, 39. Half of 39 is 19.5. So trap 2 is the sum of those two trapezoids. 7.5 plus 19.5 is 27. Okay. And that came out somewhere between left 2 and right 2, because left 2 was a big underestimate and right 2 was a big overestimate. And this one is, which is it, under or over? Over, but just by a little bit, because those lines are not, they're pretty decent approximations for that curve. All right, so it turns out that if you know left end and right end, you can find trap n easily where you don't have to actually draw the trapezoids. So trap turns out to be the average of the left and the right. So many people hypothesized when we first learned left, right, and mid that mid was the average of left and right. Turns out that trapezoids are the average of the left and the right. So let's find trap 2 using our easier formula. So trap 2 should be left 2 plus right 2 over 2. And left 2 was, can't remember, 15. Right 2 was 39 over 2. That should come out to 27. Okay, so let's compare our 27 and our 15 and our 39 to the exact value. The integral from 1 to 3 of 3x squared dx. If I want to know the exact value under that curve, I can use FTC. Find an antiderivative, plug in the bounds, and subtract. So it's an antiderivative of 3x squared. X cubed. So I do x cubed, evaluated from 1 to 3. Plug in the 3. 3 cubed is 27. Plug in the 1. 1 cubed is 1. So my exact value is 26. So you can see trap was really good. Left and right were not so good. So we write mid n if you use midpoint rectangles. draw two midpoint rectangles on the blank graph that's on the previous page to find mid 2. Okay, so I have one blank grid here. You guys go ahead and do that. Okay, so there are my two rectangles. I created an interval from 1 to 2 and an interval from 2 to 3. On each interval, you locate the midpoint, and that is the point that determines the height of the rectangle. So halfway between 1 and 2 is 1.5. Plug 1.5 into 3x squared. What do you get? 6.75, and the base is 1. So the area of this pink thing is 6.75. And then my blue rectangle, the midpoint of that rectangle is at 2.5. So plug 2.5 into 3x squared. What do you get? 18.75. So we add them to get mid 2. Two rectangles using midpoints as heights. Add those together and you get 6 and 18 is 24 plus 1.5 is 25.5. So in this case, mid was actually a little closer, right? Because the exact value is 26. Mid was a little closer than trap. Okay, we're not going to confirm our results. We know we're right. So for some functions, you can easily tell if your approximations will be an overestimate or an underestimate. So let's think about what do we know if the function is increasing, okay? Saying nothing about its concavity, but just always increasing, so it might look like that, right? The exact value will always be between what and what? Left and right, yeah. So if you use left endpoints, you'll always have an underestimate, right? And if you use right endpoints, you'll get an overestimate. So it doesn't matter what the concavity is. If it's increased, if it's always increasing, the left will be an underestimate. No matter how many rectangles you use, it'll get closer and closer to the exact value, but it'll always be a little bit under. And the right will always be bigger. How about if the function is always decreasing? Draw a little picture of that. Regardless of the concavity, I'm going to draw this picture so it's always decreasing. What two approximations will the exact value always be between? Yes, which one's smaller though? The right one will be the underestimate, right? Because let's say I want to go from here to here, two rectangles. Right endpoints will always be below the curve. So right end will always be smaller. And left end will always be the overestimate. Okay, let's think about concavity. If the graph is concave up, increasing and decreasing doesn't matter. It just has to always be concave up. So let's draw maybe x squared, or part of x squared's family. What rule will always be underneath the exact value of the curve? Or if it's easier, what rule will always be above the exact value of the curve? Trap will always be an overestimate. So let's say I just want to do two intervals like here to here. If I go up to the curve, if it's concave up, a straight line is always going to be above the curve. So it's always going to be an overestimate. So trap, when you're concave up, will always be over. Now, what do you think for under? Yeah, the midpoint if it's concave up. So if we find the midpoint and use that as my rectangle, how can you tell that that rectangle would be an underestimate? Yeah, there's more area here that I'm not accounting for than extra area I added if it's concave up. So mid will always be below. And it reverses if it's concave down. Trap will always be below, and mid will always be above. Okay, so I want you to think about this for a minute, discuss in your groups if you want. We're looking at the integral from 1 to e of ln x dx. You may want to draw a picture that shows what area that represents. Put in order from smallest to largest, mid, right, trap, left, and the exact value. Okay, so I drew a little picture up here of the graph of ln x, and I shaded the area under it from 1 to e. So the order of these guys is going to be the same no matter how many rectangles, or intervals, I should say, how many intervals I use. So let's draw for one interval, right? Mid, right, trap, left, and that's it. Yeah, the exact value. Okay, so if I wanted to use a midpoint, well, let's start with left. I think left is going to be a really terrible approximation, because if this is my one interval, I use the left endpoint to get the height, and I would approximate it with 0, right? So left is going to be a really low underestimate. So my hypothesis is that that's going to be the lowest, right? And then for right, I would approximate this area by using the height of the function at the right endpoint. And so it would be that whole rectangle. And that would have an area of E. And it would be a big overestimate. So let's put right as our hypothesis for the biggest. All right, so midpoint and trap, we got to decide which is better. So trap, is that going to be an overestimate or an underestimate? Under. So I'll draw it in here. So I would just connect these two with a straight line, and I'd be finding the area of that triangle. So trap is an underestimate. And how about midpoint? Is that going to be an overestimate or an underestimate? Over, yeah. There's going to be a little bit more area. So here's my midpoint. Yeah, it's hard to tell in my picture, but we decided earlier that because f is concave down, mid would be an overestimate. And we can clearly tell that trap's an under. So trap is an underestimate, so is left, but trap is better. And midpoint is an overestimate, so I'll have mid here. And then right here in the middle, I have the exact value. Like that. All right, we're going to jump over the challenge. So we've done pretty well approximating our curvy integrands with straight things, rectangles, and trapezoids. But we can do even better if you approximate an integrand instead of with a straight line, with another curvy thing, a parabola. Okay. So you can use a parabola to approximate a definite integral, and when you do that, that's called Simpsons Rule. Okay, he's an English mathematician, not Homer Simpson, a serious guy. Okay, so here's how you would do that estimation. So in blue, I have f of x. If I wanted to estimate the area under f of x, to use a trapezoid, right? Well, let's do each of. I'm going to draw in each of the different ways I could estimate the area underneath f of x, right? I could use a left rectangle, right? Terrible underestimate. I could use a right rectangle. Still a pretty terrible estimate. I could use a midpoint rectangle. Definitely an overestimate. I could use a trapezoid. So I could connect my two endpoints of f with a straight line and use that rectangle to estimate the area under the curve. Not very good. But instead of using a straight line between the two endpoints, right, because 2 points determine one unique line, right? Everyone remembers that from high school geometry. 3 points determines one unique parabola. So I take this interval, I find its midpoint, and now I have 3 points on my curve f of x, and I can fit one unique parabola to those 3 points. Just like any 2 points, you can fit one unique line. Any 3 points, you can fit one unique parabola. So this red curve, p of x, is the parabola that goes through those 3 points, and I could find the area under that, because finding the area under a quadratic is pretty easy. You just use the power rule in FTC. So this is how we Simpson, right, set about trying to find the area under a curve. Is he would take each interval, sort of break it into two, like find the midpoint. So he'd have 3 points on the interval, fit a parabola, find the area under that. And he would do that over every interval and then add them all up. So here's the formula that you get that is derived by finding the area under parabolas instead of the area under lines using trapezoids. Ugh, it is pretty awful, right? And I'm not going to derive it. You could all understand it. It's just like ugly and messy. But you get the idea, right? Fit a parabola instead of a line, find the area under the parabola. All right. So that's pretty awful. But it turns out that if you know trap and mid, you can find Simpsons by taking a weighted average of the two, right? Pretty remarkable that they have this relationship. So to find Simpsons, you can do twice the mid plus the trap over 3. Okay, and then you don't have to even think about parabolas, fitting parabolas and finding area underneath them. You can just use this little shortcut. So I'm not going to actually make you do the area under parabolas thing. If this is an option, you can just do this. So if I wanted to find Simpsons for the integral from 1 to 3 of 3x squared, I would do 2 times mid plus trap over 3. The mid was 25.5. Trap was 27 over 3. Now I need a calculator. Two times 25.5 plus 27 divided by 3 is 26. That actually is the exact value under the curve. We happen to hit it here. Okay. When you ask your calculator to evaluate a definite integral numerically, right, when you do that like fint, give the function x and give the bounds, it does something really similar to Simpsons Rule. It's called Gauss-Conrad quadrature. Okay, so it's a bit more complicated. It's even more efficient than Simpsons Rule, but it's pretty similar. And we are not going to look at that pretty pictures. Well, maybe we'll come back at the end if we get through everything. Okay. So Here's a kidney-shaped swimming pool measured at 2-meter intervals. We want to use Simpsons Rule to estimate the area of the pool. So first thing I would do is translate this to a set of coordinate axes. And I'm just going to like flatten out the bottom of the kidney-shaped pool. It's like I'm going to grab this piece that goes in and just pull it down so that my heights, my base is all going to be on the x-axis, and then keep the heights the same, and it should have the same area, right? It's like I just sort of pulled it, like reshaped it like that was a piece of wire. Just pull on it. So I would have 0, 0, right? And then 2 meters later, I'd have 6.2. That's 6.2. And then 2 meters later, I'm going to have 7.2. And then 2 meters later, I have 6.8, somewhere between those guys. And then I've got a 5.6. And then a 5. And then a 4.8. And then another 4.8. This is really terribly to scale, and then a 0. So this curve that I've created should have the same area as the swimming pool. Can we agree? Okay. All right, so I don't know any of the heights in between, right? They weren't given. I could guess them, but I'd rather not. So if I was going to use Simpsons Rule, to fit parabolas, I would have to use how many intervals? Yeah, at least 3. Yeah. What if I was going to use midpoint rule? How could I use midpoint rule here if I don't know the midpoints on the 2-meter intervals? Yeah, so I could make my intervals 4 meters wide, and then I could use one of the points I know as the midpoint. So let's do that. Let's see, because it just says use Simpsons rule. It doesn't say how many intervals I have to use. So if I make my intervals 4 meters, I've got 1, 2, 3, 4 intervals. Okay, so if I want to find Simpsons with 4 intervals, I need to use trap and mid with 4 intervals. The only way I can use mid on this information is to use 4 intervals. So this would be twice mid 4 plus trap 4 over 3. Right. So you guys set about doing that. Find Simpsons approximation over the 4 intervals. Okay, so we need mid and trap to be able to find Simpsons. So I've already broken this into 4 intervals. So if I'm going to find mid over the interval of length 4, so I use the midpoint to get my height of that rectangle. So this is 4. This is a height of 6.2. 4 times 6.2 is 24.8. Okay, so then you got to do that over each interval. Oops, that's not my, yeah, it is. Okay, so that is at a height of 7.2. 4 times 7.2 would be, oh, you're right, yeah, that's another, that's 6.8, yeah. So 4 times 6.8 is 24 plus 4 times 0.8 is 3.2, 27.2. Okay, so then my next interval, here's my midpoint. base is 4, that rectangle is at 5. 5.0 times 4 is 20. And then for my last interval, that midpoint is at 4.8. So 4 times 4.8, so that's 16 plus 19.2. Okay, so then you add them up. Just to make sure I don't make a mistake. 24.8 plus 27.2 plus 20 plus 19.2. Okay, so 91.2. So that's my mid with 4 intervals. Then I'm going to find trap with 4 intervals. So I'll use another color here. So for trap, I have to use the same width. So I have to take the endpoint at each piece, the endpoint at each interval, at each end of the interval, and connect it with a straight line. So here I end up with a triangle that has base 4 and height 7.2. So 7.2 times 4 divided by 2. 14.4. Okay, so then my next interval, take this point and this point, connect them with a straight line. And I've got this trapezoid. Anybody already have its area? Thank you. 25.6. And then my next interval, this point and this point, connect them with a straight line. And I have this trapezoid. What's its area? Say it again. 20.8. And then in my last interval, I get a triangle. And what's its area? Good. All right, so I add those up. 14.4 plus 25.6 plus 20.8 plus 9.6, 70.4. Okay, so then Simpsons is twice the midpoint plus the trap over 3. 2 times 91.2 plus 70.4 divided by 3, and I get 84.3. Simpson's estimate of the area of the pool. Okay, so far we've been estimating the area under a curve by calculating the sum of the areas of right rectangles, left rectangles, midpoint rectangles. And then you can use those formulas to give estimates for trap and for parabolas. So these two formulas, trap n and simps n, if you aren't, they only work, these two shortcuts for trapezoid and Simpsons, they only work if your interval is cut into pieces that are all the same length. Okay. So if they aren't, then you can't find Simpsons approximation or the trap approximation using those two formulas. You have to actually draw the trapezoids and actually find the parabolas. So here's an example where I just have points and I don't have a function and they're not placed at equal intervals. So in the swimming pool problem, I was able to use my shortcut because those were equally spaced intervals, 4 of 4. So now these aren't equally spaced. So if I want to find trap and Simpsons, I have to do it by hand. So luckily there aren't that many points and it won't take that long. But if I want to use left rectangles, I would just use, and what am I finding? The area under the curve whose values are given in the table. So it didn't give me anything about 0. Okay, so let's just go from 1 to 7. So I'm looking for the area under f of x from 1 to 7. So if I use left rectangles, I'm going to get something like this. Oops. I have to go all the way to my next point. Otherwise, I won't have anything to estimate in between. Oh, I guess that's it. Okay, so then I just have to add these up. This has area 1 by 2 is 2. This is 2 by 4, which is 8. This is 2 by 3, which is 6. And this is 1 by 3, which is 10. So it's 19. And if I want to use right rectangles over each interval, I use the right endpoint over each interval that I know something about. So then I'll have this one, and then this one, and then this one. So my pink rectangles now are 1 by 4 is 4. This is 2 by 3, which is 6. 6, and this is 1 by 1, which is 1. 10, 16, 17 for my right rectangles. And I think I need to erase, right? I don't think I can draw anymore on top of here. Everybody okay? All right. Okay, so if I want to use midpoints, let's see. Can I? I can't really, because I don't, if I use the intervals that are naturally there, you know, between each point, I don't know the midpoint. So if I extend it to the next point, that's not the midpoint. It's just a random point. So I could use my random point if I wanted. That would be like a variation on midpoint, but I can't really do it. But I can use trapezoids. So over each interval, I can connect my points with a straight line. And then I can find these areas. I could use a trapezoid formula or break it into rectangles and triangles. I'm going to do that because it's just easier. Okay, so this is 1 by 2, 2. This is 2 by 2, 2 by 3, 6, 6, 1. And then my triangles, this is 1 by 2, so that's 1. And this is 2 by 1, so that's 1. This is 1 by 2, so that's 1 also. So 6 and 6 is 12, 14, 15, 16, 17, 18 using trapezoids. All right, so finally, we got to use parabolas. Everybody got this? Okay. So for every 3 points, that's going to be 1 interval because I need 3 points to determine a parabola. So each set of 3 points is going to be 1 interval, and I'm going to fit a parabola to those 3 points. So I've really only got 2 intervals here, 1 to 4 and 4 to 7. Do some different color. So I have to fit a parabola to the 3 points there. 1, 2, 3. So I could try to eyeball it. It's kind of hard eyeballing the parabola that'll fit 3 points. Yeah, that's pretty terrible. I could do it algebraically, right? I have 3 points. How many parameters does a typical quadratic have? 3. A, B, and C, and ax squared plus bx plus c. So you have 3 unknowns, you have 3 points, you could set up a system of equations and solve them. Or you can make your calculator do it using regression, because 3 points will determine one unique parabola. So we'll just give the calculator those 3 points. I don't want that. I want stat, edit, list, clear these. All right, so then I'm going to give my x coordinates. I have 1, 2, and 4 as my x coordinates. And then my y coordinates are 2, 4, and 3 that go with those x's respectively. Okay, so now I'm going to have it fit a quadratic. I'm just going to do a quad reg. So stat, calc, quadratic regression. So I could, but the more intervals I use, the better an approximation I'm going to get. Just like with rectangles, the more rectangles you use, the better approximation you get. So the most I could use is 2, because you need 3 points on an interval. So I'm using 2. And if I used 1, right? If I used one big interval, then I would only use the 3 points. I would only fit 3 points. So that's what Simpsons Rule does. Yeah, that's just not Simpsons. Yeah, and is that that looks like a quartic that you graphed there? Yeah. Yeah, so that's another method, is to fit a polynomial to as many points as you can, and then find the area under that. Okay, so let's see. I'm going to do list 1, list 2, store it in y1. Okay, so here's my parabola, negative 0.833 x squared. I'll do this in pink. Plus 4.5x minus 1.67. And you can see the r squared value is 1, which means it's a perfect fit. That will always happen if you have 3 points, right? 3 points determines one unique parabola, so you'll always get a perfect fit when you put in 3 points. And then let's just take a quick look at it. Zoom 9 will show me my... I'm doing the 3 on the first interval. I'm fitting one parabola to the first 3, then I'll fit another parabola to the second 3, find the area under each parabola, and add it up. So those are my 3 points, and I fit a parabola to it. So it looks like the peak is somewhere like right here, and I get this and this, something like that. So I want to find the area under the pink parabola from 1 to 4. And I can use that, I can do that using FTC too. All right, and then for my second interval, I'm going to have to find a different parabola for those 3 points and find the area under that. So I'm going to go stat, edit, maybe you guys should do this one. Find the parabola under the second interval, get the area underneath it, and then add these together. Okay, so I did the regression for the second 3 points, second set of 3 points to fit a parabola. So you end up with negative 0.67x squared plus 6.67x minus 13. Again, it's a perfect fit. It'll always be a perfect fit if you only use 3 points. So, little aside, 2 points determine a line, 3 points determine a quadratic, 4 points determine, what do you think? A cubic. 5 points determine a quartic. Yeah. So you could get more and more sophisticated by fitting higher and higher polynomials, which is what you did. Yeah. Yeah, so we only had 5 points, so you could have fit a perfect fourth degree polynomial, which is what you did. Yeah. Fourth degree polynomial. Yeah. But that's just not Simpsons rule, which is what we're doing. Okay, so I wrote down my formula here. So basically, I fit a pink parabola to the first 3 points and the blue parabola to the second 3 points. This is what it looks like on your calculator. And then I'm going to find the area under each parabola using FTC 1. So I want to find the area from 1 to 4 under the first parabola. So I'm looking for that. And then under the second parabola, I'm looking for the area from 4 to 7. So I'm looking for this area here. So I'm going to take the integral from 1 to 4 under negative 0.833x squared plus 4.5x minus 1.67 dx plus the integral from 4 to 7 of y2. And you can use FTC because those are quadratics. You can easily just use the power rule to get an antiderivative. And we're out of time, so I'm not going to do it.